All right, you guys. Hey, welcome back. Today we're beginning Unit 1.2, Chemistry and Living Systems. And we are beginning with Part 1, which is the Intro to Biochemistry. Now, a lot of times kids ask me, why do we study chemistry in biology? And are simply put, because of that one word in the title, biochemistry. We're looking at how chemistry occurs in living things and how it affects living things and actually allows, well, living things to live. So before we move on, I do want to draw your attention to more or less, kind of sort of not really center of the screen, is one of my favorite science related, specifically chemistry related jokes. Never trust an atom. They make up everything. That's a knee slapper. All right, so without further ado, let's get started, shall we? All right, so here we are. We're going to start with a little bit of chemistry introduction. So first we have to discuss, okay, well, what is chemistry? We said biochem is chemistry in living things. All right, so then what is chemistry? Well, simply put, well, I guess not so simply put, it's the scientific study of the properties of matter, the composition of matter, and the ways in which different substances will react. So breaking that down, it means that we look at the properties, so the different characteristics of stuff. What makes water act the way it does? What makes this table act the way it does? What makes air act the way it does? The composition of matter. So what is the stuff made of? What is air made of? What is the table made of? What is water made of? And the ways in which different substances will react. So what happens if I take this substance and this substance and I put them together? Will they mix? Will they create something completely new? What's going to occur? So chemistry looks at the characteristics, the makeup, and the reactivity of different things. Now, an atom, we consider this the smallest basic unit of matter, meaning that anything that is made up that is matter, like tables and air and water and us and my dog Ripley, all of that is made up of atoms. Now, yes, atoms are made up of smaller things. We'll get to that in a moment. But on their own, those smaller things cannot come together to form stuff. Only when they come together to form an atom can atoms come together to form bigger stuff. Everything is made up of atoms. The only things that is not made up of atoms are not matter. So for instance, energy, heat and light and all that, that's pure energy. It is not made up of a tangible substance. It can affect matter, but it itself is not made of matter. Therefore, energy is not made up of atoms. But everything that is matter is made up of atoms. All right, so why do we call them atoms? Well, it comes from the Greek word atomos, meaning unable to cut. And that's actually kind of impressive because, first of all, you cannot see atoms with a basic light microscope like we use in science classes today. But thinkers and philosophers and early scientists were able to figure out that atoms had to have existed and they had no way of seeing them. They had no way to prove that they were there. And that's why they use the term atomos, meaning unable to be cut, because they actually thought the atoms, these small invisible things that make up everything, must be the smallest possible thing there is. We know today that it's made up of smaller pieces, but it's still impressive that way back in the day, they were able to actually figure out that all matter had to be made up of something that could not be seen with the naked eye. All right. So let's move on to something called elements. Now, a lot of us have seen elements in the periodic table, or we know some of them like oxygen or carbon or hydrogen. And what an element is, it's a pure substance that consists entirely of one type of atoms. Now, we arrange the atoms that we have figured or found or created in a lab. We arrange them in the periodic table. Now, the periodic table doesn't really look all that useful at first. It looks like a weird shape, but in all honesty, it's arranged that way, the table is, because it allows us to make predictions on patterns. So it's arranged so that similar grouped atoms are together, and this allowed us to make predictions on previously unknown elements and what their characteristics would be. Let's take a look at a periodic table to kind of demonstrate that. So this is a standard periodic table, nicely color coded. It is up to date. Even as much as a few years ago, these ones down here, 113 to 118, were not known. Actually, I think when I was teaching in my last school, which was about 5 years ago, at this point, it's 2020 now, I think only MT 109 and 110 were the last ones that were on most periodic tables. But anyways, I digress. You notice how this one is color coded, and that's because it's color coding different groups. So we have our alkali metals, we have the alkaline earth metals, transition metals, the other metals. These are the metalloids, also known as the semiconductors. Here, kind of reddish color, we have the nonmetals, then we have the halogens, and here we have the noble gases. Down here, if you notice, we have 57 through 71, and that would fit right here. We do call these the lanthanide series, and then underneath 89 to 103 is the actinide series. And the reason why they're oftentimes put at the bottom is because imagine if we left them right there. It would make the periodic table so long that it would really be very difficult to put into a textbook and look at it very easily, especially for children who are still learning about it. Now, let's see. You'll notice that there's a lot of numbers. Let's come up here for a moment to the example. This is a symbol, and that's the name. So the name of one type of element is platinum. The symbol is capital P, little t. And the atomic number is very, very important because remember how we said that elements are made up of one kind of atom. Well, the atomic number tells us that, and it's related to the number of protons. We will get to this in a moment, but essentially every single atom of platinum has 78 protons. So that's what the atomic number tells us. The average atomic mass is looking at all possible atoms of platinum and what their average mass would be. And we'll get to that in a little bit. So here's a periodic table. As you can see, it's organized. The light colors mean that they have similar properties. Let's move on. Where's my little, there it is. There we go. All right. So now let's talk about the subatomic particles. As we said, atoms are made up of smaller particles. Now there's three main ones, the electrons, protons, and the neutrons. A lot of times we show pictures like this in the bottom where you have the center portion and then the rings around it. Now this is not an accurate depiction, but it is a visual way to kind of help people start to understand what's going on. Now, first off, there are two regions. In the center, where you see this clump of circles, that's called the nucleus. It is the center of the atom. And within the nucleus, you find two subatomic particles. We have the protons and we have the neutrons. In the outer portion, we call this the electron cloud. Now, the electron cloud is simply the region of space around the nucleus where you are likely to find electrons. We do like to draw them as if they're orbiting the nucleus like planets. We have found that is not accurate, but it's still an easy visual for us to show. All right, let's start talking about these subatomic particles, shall we? All right, so first we have protons. Remember, protons are found in the nucleus, and protons have a positive charge. Now, the number of protons in an atom for a particular element does not change. Changing the number of protons changes what element that atom is. So that's why we use this as our defining characteristic for an element based on, okay, what is the number of protons? That will tell us what element a particular atom is. So this will stay the same if you're trying to identify an atom. So for instance, carbon has 6 protons. Every single carbon atom everywhere has 6 protons. And we call this the atomic number because it is such a defining characteristic. Because of that as well, that's why we also put it in the periodic table. So here's another example from boron, or from the periodic table. It's boron, capital B, and usually somewhere around the top, either the middle or often one of the corners, is the atomic number. See how it says 5? That's the atomic number for boron. It tells me that there are 5 protons in boron. All right. Now, sometimes that can also be the number of electrons or neutrons. Not always, though, and we'll get to those cases later. But this atomic number tells us the number of protons. So as long as you have a periodic table and I ask you, all right, how many protons does this particular element have? You should always be able to tell me. All right, neutrons. So neutrons have no charge. They are neutral. You can even tell because the first 5 letters are the same. N-E-U-T-R, N-A-U-T-R. Neutrons are neutral. They are roughly about the same size as a proton. So when we consider the mass of different atoms, we look at the numbers of protons and neutrons. Electrons are actually so tiny that their mass is negligible. That's why we only take protons and neutrons into consideration when we discuss the mass of an element or of an atom. So since we only look at those two, I can actually figure out the number of neutrons in an atom if I know the mass of the atom and I know its atomic number. And it's simply, as we're going to describe here, based on subtraction. So, as I said, we figure out the mass by looking at just protons and neutrons. So protons plus neutrons equal the mass of that atom. Therefore, if we rearrange it, then the mass minus the number of protons should give us the number of neutrons. So it's all about subtraction. Now, if I give you the mass number for a particular exam or a particular atom, you should use that. But if I don't give it to you, like for instance, you can use the atomic mass. Now, as I said before, that is the average of all possible atoms for that element, meaning that there are, notice how it's a decimal, there are atoms of boron that do not have just 5 neutrons. A lot of times what we might expect is the atomic number might also equal the number of protons and neutrons. So in this case, 5 protons, 5 neutrons, 5 electrons. But this atomic mass tells me it's not. So what this is, this takes in all possible atoms, even when they have different numbers of neutrons, and figures out the average. So if we round that up to 10.811, rounded would be 11. 11 minus 5, because that's the number of protons. So 11 we got from the mass, 5 we got from the atomic number. 11 minus 5 is 6. So typically, mostly, on average, most boron atoms will have 6 neutrons. Now, is that always the case? No, sometimes they have 5, they might have 7, and that atomic mass looks at all the possibilities. Now, what do we call it when there's an atom with a different number of neutrons than we would expect? We call them isotopes. So remember, the number of protons never changes because that defines what element that atom is. But if you change the number of neutrons, if it's something that you wouldn't necessarily expect, then we call that an isotope. So for instance, remember we said ideally, whatever the number we have for protons, so whatever our atomic number is, we should see for all the other subatomic particles. So carbon here, the first example, it has an atomic number of 6, so that means 6 protons. Ideally, in a perfect world, you'd see 6 neutrons and 6 electrons. Well, you notice here that we still have carbon, but we added something to the name, carbon 13. So what this tells us is that this is an isotope of carbon. And if we were to look at this, that 13 is the mass of this particular atom. So 13 minus 6 for protons gives us 7. This particular isotope has 7 neutrons. And here we have carbon 14. So again, I'm giving you the mass for this particular atom. It has a mass of 14 minus the 6 protons, and we get 8 neutrons. So this isotope of carbon has 8 neutrons. So notice how there's different types of carbon molecules. In every single one, the carbon atom has 6 protons, but the number of neutrons changes, and that changes the mass. All right. Well, now let's talk about electrons. So electrons are super duper 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 tiny. I mean, we're saying how small atoms are, and now we're talking about how protons and neutrons are even smaller than that. But electrons are even smaller than protons. They are so super small that their mass is actually considered negligible. So meaning that it doesn't really affect the overall value when we look at the mass. So instead of the mass of carbon 14 being 14, it might be 14.000000001. Very tiny. Let's see. So as we said, they move around in what we call the electron cloud. That's just the region around the nucleus where electrons are going to be found. Now, the thing about electrons is they have a negative charge. And despite their super duper small size, the strength of their charge is equal to that of protons, but it's opposite. And just like with magnets, when you have two things with the same charge, they're going to repel. So if I was to put 2 electrons near each other, they would push each other away. But if I put a positive proton and a negative electron close to each other, they will attract because they have opposite charges. And sometimes we can get what are called ions. Now, ions are what happens when an atom gains a charge. Now, normally, a lot of times, atoms are neutral. And what that means is that they have the same number of protons as electrons, so that the charges balance out. So an electrically neutral atom has the same number of same number of protons as electrons. So in carbon, it has an atomic number of 6. That means it has 6 proton elements. So carbon has an atomic number of 6. It has 6 protons. And if it's neutral, that means along with the 6 protons, it also has 6 electrons. But there are cases where certain atoms can lose electrons or gain electrons. So if it gains electrons, even though we talk about gain, and don't think of it like addition and subtraction because we're going to use positive and negative signs. So if you gain an electron, remember the number of protons never changes. So if I'm gaining extra negative things added to me, I'm going to become a negatively charged atom. And this negative ion, an ion is simply an atom with a charge on it, or a molecule with a charge on it. A negative ion, we call that an anion. You can see that term right here. And it has an overall negative charge because it has more electrons than protons. Remember, the number of protons doesn't change. So to have more electrons than protons, you have to have extra electrons added to you. So you become negative. Now, well, what if we lose electrons? What if they're lost and they're removed from us? Well, then we have more protons than electrons, meaning we have more positive things than we do our negative electrons. So we actually gain an overall positive charge. And a positive ion, we call that a cation. You see that term right here. And the reason why, again, it has more positive protons than electrons, because some of the electrons left the atom. They actually separated from the atom. So that'll give it an overall positive charge. I do have a video that talks about it explains more about ions and isotopes and how to solve questions involving those. Get to that later though. All right, compounds. Compounds are formed when elements combine with other elements. So a lot of times this also begs the question, how are compounds different than molecules? So a molecule is when more than one atom bond together. A compound is when you have more than one element bonded together. So oxygen gas is O2. There are two oxygen atoms bonded together. That is a molecule. It is not a compound because it still only has oxygen in it. A compound would be something like water, H2O. It has two different elements in it. It has hydrogen and oxygen that are bonded together. So water is a compound because it has different elements. It's also a molecule because you have multiple atoms. All right, so we can show that atoms contained in a compound and their proportions with something called a chemical formula. So it doesn't exactly show it all that well in Prezi, but for instance, chemical formula would be H2O water. Now, typically that 2 would be a subscript. So it'd be smaller and behind the hydrogen near the bottom of the H. So it's like H2O. And table salt is NaCl. Now what these tell me, it tells me exactly which elements are present and in what proportion. Going back to H2O, which is water, that tells me there are 2 hydrogen and 1 oxygen. The fact that we wrote the O means there's an oxygen. And since there's no number behind it, that tells us there's only 1. NaCl, that tells me there is 1 sodium atom bonded to 1 chlorine atom. Now, the physical and chemical properties of the compounds can be very, very different than the elements they contain. For instance, table salt, NaCl, very tasty when added to food. It's like this little crystal whitish color, whitish clearish color. But sodium on its own is a solid metal that is very, very highly reactive with water, meaning you add pure sodium to water, it will explode. And chlorine on its own is a poisonous gas. So we have this poisonous gas plus this explosive metal, but when they bond together, we have a rather tasty addition to food. So again, the properties are very different. It looks different, so the physical properties are different, and it behaves differently. I could put salt in water, it will not explode. I don't have to worry about breathing it in as much because it's not a gas. So we see how the properties have changed and as a result. So let's talk about some of the ways we can bond. So first off, we have ionic bonding. So ionic bonding is when 2 atoms bond together due to both of those atoms being ions, meaning they have a charge. So if you look at the picture, how this works is essentially one of the atoms loses an extra electron. So it loses an electron, giving it a positive charge, like here with our sodium. Here, chlorine gains, it picks up that free-floating electron and adds it to itself. So it gains an extra electron, giving it a negative charge. So we have a positive charged atom and a negative charged atom. And just like magnets, when you have a positive and negative, they attract, and that attraction will actually keep them bonded together. All right. So let's take a look at a picture a little bit closer up. So again, here we have sodium and chlorine. We have this electron here is actually going to physically leave the sodium, and whether it's this electron or another electron is going to be added here. So if you notice, no more electron in the outer layer. So it has lost an electron, it is positive. This here we have chlorine, it has gained an extra electron, making it negative. Positive, negative atoms bond together, and we call that an ionic bond. Sorry. So covalent bond is when electrons are actually shared instead of being lost. So we saw before in an ionic bond, the electron physically left one atom and attached itself to another. But in this case, we use one electron at least from each atom, and they're kind of put in a common area between them so that both atoms have use of it. So if the atoms each share one electron, meaning there are two shared electrons, one from each of them, that forms a single bond. If they were each sharing two electrons for a total of 4 in that area, it would be a double bond. So when they each donate one electron to this zone of sharing, it makes a single bond. So for every 2 electrons total, 1 from each, so that's 2, you get 1 bond. So picture, here we go. As you see, it says that the red ones are from the hydrogen, the blue ones are from the carbon. So carbon has 4 in its outer layer. It can hold up to 8 though, in order to make it the most stable. Hydrogen has 1 in its outer layer. It can hold up to 2 to make it stable. So what happens is the carbon shares 1 electron with this hydrogen, and this hydrogen shares its 1 electron with the carbon. So now this hydrogen has access to this and this electron. Same with here, same with that hydrogen, same with this hydrogen. And since the carbon is also sharing with each of the hydrogens, that means the carbon has access to this and this, and this and this, and this and this, and this and this electron. So it has access to 8 electrons now. So this is just a picture to kind of show you the bit more of the differences. I'm gonna put this down here where it's out of the view. Between ionic versus covalent bonds. So here you see 1 electron in the outer layer, here you see 1, and we see the same thing here. So we're kind of starting out with the same idea. In ionic, this electron leaves and joins up with this one. So what we get is this ion is positive because it's missing an electron. This ion is negative because it has an extra electron. And it's those positive and negative charges that cause it to bond. Whereas here, starting with the same thing, each one has 1. And what happens is they both have access to those electrons. So they're not actually being moved from one atom to another, just simply put in between so that both atoms can use them. And that's covalent bonding. All right, let's put this back up here. Now, van der Waals forces, we're not going to talk a whole lot about because we're going to kind of jump to it in water as well. But this is a form of intermolecular attraction. So it's a force of attraction between molecules, between compounds. So atoms in a molecule do not always share the electrons in covalent bonds evenly. So what that means is that on one side of, if you look down here, atom A, because of how the electrons are distributed, you might end up with the electrons mostly on one side of the compound and not as much on the other, giving one side a slightly more negative end and the other side a slightly more positive end. We call this being polar or having polarity. And what happens is a slightly negative end could form an attraction with a slightly positive end of another molecule. Now it's weak. A lot of times they're very easily broken, but it's what helps hold compounds together to form a larger structure. So they are very, very weak. They're a lot weaker than covalent and ionic bonds, but they can still hold things together up to a point. That's actually why, you see this cute little gecko, why they can defy gravity, why they can climb so easily on glass and like even hang upside down from the glass. It's because their toes form this attractive bond due to van der Waals forces, that's just what we call it, between their toes and the glass, and it forms this attraction between us. So it's almost like when you have little tiny magnets and you stick them to a fridge and they just kind of get stuck there. There's nothing actually sticky on it. It's the hold, the attraction between the magnet and the fridge. It's the same thing with the toes of the gecko and the glass. It's this force of attraction that's allowing it. So this is showing us water molecules. Water is a very polar molecule. Because of a higher concentration of electrons on the oxygen, this side of the water molecule or water compound is still a molecule. Sorry, of this water molecule gets a more negative, slightly more negative charge. And because there's not as many here on the hydrogen or here on that hydrogen, it's slightly more positive. So this hydrogen will form a weak attractive force with the negative part of the of the oxygen, and that is this weak force we're talking about. Now we call this hydrogen bonding because it involves a hydrogen atom. We will come back to this again in our properties of water lesson. All right, so now let's just kind of discuss additional sources. These are great to, extra sources done by me and other people to kind of further help you understand. So I have a Science in Pajamas video on the atomic structure. We're not actually going to watch it now, but it's there for you. We have one on further explanation on ions and isotopes, as well as how to solve some of the types of questions I'll ask you about in our class. Chemical bonding, so we talk about ionic and covalent bonding, as well as van der Waals forces. We also talk about the Bohr's model and how to draw a Bohr's model. We're not going to do a whole lot of that in class, but it might be helpful for you to have a basic understanding before you get to chemistry. And then finally, we have chemical and physical changes, where I do some demonstrations to kind of show you the difference between those. All right. And then the other videos include, we have Ricochet Science, Structure of an Atom. We have Science Geeks, Atomic Structure, looking at atoms, ions, and isotopes. So it kind of goes into a little more detail on all of those. Ricochet science again, chemical bondings, ionic versus covalent bonding. So a good resource to kind of look at how those are different again. We have Socratica, which looks at 4 types of chemical bonds, and this one does include the van der Waals forces, so that's why I included it. Boseman science, the Bohr atom, and then we have Spot Channel looking at chemical and physical changes. So in the description, I'll post a link to the actual Prezi. This way you have access to all of the videos. But yeah, I mean, I hope this helps you guys further understand what we're doing in class. And until next time, you guys, just be awesome and amazing. Stay safe and stay healthy, you guys. All right. Bye. Bye.